This map shows the tectonic boundary between the Caribbean and North American plates. On January 12, 2010, a magnitude 7.0 earthquake ruptured exactly here, violently shaking the Republic of Haiti. The resulting devastation was catastrophic. Over 217,000 people were killed, and 1.2 million residents were displaced among the ruins of Port-au-Prince. A magnitude 7.0 earthquake is a major geological event, but it is not rare. The planet averages about 15 quakes of this size every year, yet they rarely produce this level of mass casualty in modern engineered environments. Port-au-Prince suffered extreme, disproportionate devastation compared to similar seismic events worldwide. The answer requires looking past the top-line magnitude. To understand this disaster, we must treat it as a complex, multivariable engineering equation. The first variable is the seismic source itself, an abnormally compact, intensely concentrated energy release. The subsequent variables are the vulnerable alluvial soils lying directly beneath the city and a built environment engineered with almost zero lateral force resistance. To understand the true cause of death, we must trace the precise path of that energy, starting deep within the crust at a blind fault rupture and following it upward until it shatters the failing concrete columns of the city. We begin at the geological baseline. The Enriquillo Fault is an active strike-slip boundary running right through the southern peninsula of Haiti. But when reconnaissance teams surveyed the area immediately following the 2010 event, they found zero evidence of surface rupture anywhere along that mapped fault line. This lack of physical tearing at the surface indicates the slip happened entirely underground, likely on an unmapped blind fault strand running adjacent to the main boundary. This is the USGS finite fault model. It maps the exact distribution of tectonic slip across that subsurface fault plane. The concentrated red and orange areas indicate maximum slip. This active zone measures roughly 15 kilometers deep by 30 kilometers long. That surface area is remarkably compact, measuring roughly 1/3 the size typically expected for a magnitude 7.0 energy release. Forcing that massive amount of tectonic energy through such a highly restricted space changes the mechanics of how the fault moves. Instead of a prolonged release, this spatial compression forced an incredibly abrupt and sharp rupture event. The vast majority of the fault's moment release occurred entirely within the first 10 seconds of the slip. This sudden, violent energy spike generated highly destructive, high-frequency seismic waves. The city took the full impact of an ultra-condensed blast of high-frequency kinetic energy, concentrated into a single violent 10-second spike. As those high-frequency waves traveled upward, they encountered the specific soil profile resting right beneath Port-au-Prince. The city sits directly on the cul-de-sac plain, a deep geological basin filled with Holocene alluvial fan deposits. These deposits consist of unconsolidated gravel, sand, and clay, reaching depths of up to 200 meters. This graph shows acceleration data from 2 seismographs. The top traces, recorded at the U.S. Embassy on deep alluvial soil, show a long duration of shaking. Compare this to the bottom traces from Oliver Elementary, a hard rock site, showing a much shorter burst. The deep alluvial basin acted as an acoustic amplifier. It trapped the seismic waves, modifying their frequencies and significantly prolonging the violent shaking. Under prolonged vibration, water pressure forces saturated soil particles apart. The solid ground temporarily behaves exactly like a flowing liquid, a process known as liquefaction. This loss of soil strength had severe physical consequences for the heavy infrastructure resting on top of it, specifically the vital port facilities located on the water. The main port's North Wharf suffered a catastrophic collapse, instantly cutting off the delivery of heavy relief supplies to the city. The failure here was driven by liquefaction-induced lateral spreading. The liquefied soil physically tore apart and slid horizontally toward water, dropping the pile-supported pier down with it. Before a single building's structural integrity was even tested, the deep basin had already weaponized the seismic waves, stretching their duration and turning the city's foundation into a fluid liability. That brings us to the final variable of the equation, the engineered structures resting on top of that amplified soil. According to Haitian government statistics, 71% of all multi-story homes and apartments in the area featured heavy concrete roofs. The standard Haitian structural frame paired thin reinforced concrete columns with a massive concrete roof slab, utilizing concrete block masonry as infill walls. The problem begins with the mass at the top. As the ground aggressively accelerates, the heavy roof tries to remain static, generating immense lateral inertial forces dragging across the frame. The masonry block infill provides stiffness, but is highly brittle. It absorbs the initial shock, but shatters quickly as the frame severely deforms back and forth. The moment those stiff infill walls blow out, the entirety of that massive lateral shear demand is instantly transferred directly into the concrete columns, and this is where the system collapses. The structural columns categorically lacked the necessary reinforcing details, specifically proper steel shear stirrups, required to handle sudden, immense lateral loads. This flaw scaled up to cause macro-level devastation at facilities like the Hotel Montana, where the columns failed and the heavy concrete slabs pancaked. We can validate this mechanical failure by looking at the structures that survived. Post-earthquake surveys revealed that buildings constructed with lighter timber or sheet metal roofs performed significantly better because they generated far lower inertial mass at the top of the frame. The massive collapse of the building inventory resulted directly from an architectural typology uniquely configured to catch lateral momentum and succumb to rapid, brittle failure. The devastation in Haiti is the product of a brutal, compounded equation: a uniquely compact energy release, multiplied by deep basin amplification, multiplied by heavy, unreinforced concrete construction. Evaluating any single one of those factors in isolation fails to explain a death toll exceeding 217,000 people. It required all three factors aligning perfectly. Understanding this equation is critical because the geological threat remains active. Historical records show the Enriquillo fault system operates on a persistent, violent cycle, having previously leveled the region with massive quakes in 1751 and 1770. Reconnaissance teams issued a stark warning: an earthquake of magnitude 7.0 or larger could strike southern Haiti again at any time. The core engineering takeaway from this disaster is that surviving the next rupture does not require exotic or prohibitively expensive construction methods. The minority of concrete structures that actually survived the 2010 shaking did so merely because they possessed adequate stiffness and standard steel reinforcing details. Implementing simple, sound engineering practices, like opting for lighter roof materials and properly tying columns, is the ultimate defense against this recurring natural hazard. The 2010 Haiti earthquake serves as tragic proof that we cannot stop tectonic forces from snapping deep within the crust. But it is entirely our engineering choices on the surface that determine whether an earthquake becomes an apocalypse.